Thank you all for coming. I am Lisle. I'm a postdoc at Virginia Tech, and I'm here to be the session chair for PS25 Data Visualization and Immersive Analytics. We got four papers that look actually pretty good. I'm excited to hear and see these presentations. And okay. So when you all ask your questions, I would really like you to announce your name and your institution before you ask the question so that the speaker can identify you, maybe talk to you later. That would be really helpful. And also, yeah, we like to get names, faces connected to each other. So the first paper up is Immersive Focus and Context Techniques to Assist in Interpretation of High-Density Forest Point Clouds, presented by Spencer O'Keefe. So Spencer. The floor is yours.
Okay, so thanks for the introduction, and special thanks to my co-authors Bruce Thomas, Jim O'Hare, Jan Rombouts, Michelle Balasso, and Andrew Cunningham. Our motivation and problem area is silviculture. So this is the sustainable management and growth of forests. Oh my God, I'm going completely blank. Oh my goodness, apologies. Trees are incredibly complex, and managing them for end goals such as resource production, biodiversity conservation, and recreation is an incredibly complex process. Factors like soil health, wind, erosion, fire all play a role in forest management, as well as tree structure. Trees are infinitely complex, and the trees around them influence how they grow, as well as the trees adjacent to those too. So processes like tree selection, the process wherein trees are selected as candidates for removal in order to keep the tree forest population at a sustainable level, is a difficult problem to attack without a complete picture of the forest. There are different methodologies for getting a complete picture of the forest. One that's become more popular in the last couple of decades is LiDAR scanning. So light detection and ranging, or LiDAR, is a process, for those unaware, whereby pulsed light is used to produce a 3D structural picture in the form of a point cloud of whatever you happen to be scanning. In the case of forestry, that lets you get a snapshot of a forest at a picture in time. So a toolkit like the Emerson hover map that I'm wearing here can produce a sub-millimeter accurate point cloud of a forest that's a hectare in size in the time it takes to walk you around in a spiral. And given that forest inventory is mostly structure, this is of considerable interest to silviculturists, as it means you can get an objective, complete picture of the forest in the same time that in previous methodologies you would be able to measure a representative subsample and then scale up. The problem becomes how do you portray these snapshots to operators? How do you operationalize them, and how do you present them to humans? We think that VR is a useful candidate for doing this kind of analysis. So our research, linked to our research aim, how do we leverage VR to support dense forest point cloud tasks, such as is needed in forest management? This informed our two research questions, each of which informed its own user study, these being what are the relative strengths and weaknesses of VR over desktop displays for LiDAR analysis, and how do we design LiDAR visualizations to best support forest management tasks? Immersive analytics is no stranger to complex data visualization. Such toolkits are quite adept at visualizing relationships and relative processes in 3D space, such as in the Mnemomics project by Mays et al., who use a Leap Motion VR headset to interrogate 3D molecular datasets. Likewise, they're also useful for contextualizing fine detail and abstract matrix of complex datasets, such as in Gol et al.'s IMNDT, a workspace for non-destructive testing data physicalization. In both instances, complex structural information is made easier to pass through immense 3D visualization. There's also precedent for using VR for forest inventory, such as in the work by Chen et al., who explored human-in-the-loop feature marking for AI-based inventory assessment. As VR gives you a complete structural picture of a forest, it makes having human-in-the-loop to assess outputs far more practical. There hasn't, however, been a direct comparison between VR and desktop displays for understanding of LiDAR point clouds in a forestry context, which is what we sought to amend with our first user study. We asked participants to assess a series of forest point clouds and asked them a series of comprehension questions, so which tree is the biggest, which tree has a split stem, and so forth. We got them to do this once in VR using a MetaQuest Pro, and once again using a desktop with an equivalent resolution, using an identical control scheme. We counterbalanced for condition order and for task description, and compared the results to get a read on the relative strengths and weaknesses for VR and desktop at these tasks. We ran 24 participants, and what we found is that VR is better than desktop for basic tree comprehension. Specifically, participants are more accurate in their assessments using virtual reality. They also spend less time looking at trees before entering their answers. In other words, they're faster in VR, and they overwhelmingly prefer using VR as well. We did, however, from observations from these studies and from participant feedback, identify a series of challenges before we can operationalize these kinds of analysis. These being obfuscation, in that, as in the real forest, with dense forest point clouds, trees block trees. The other issue being performance. We could comfortably render about 10 million points on a MetaQuest Pro tethered to a laptop. Anything more than this started to cause performance lag, motion sickness, and nausea. So we needed a method to address both of these issues. Where we landed was to build on the focus and context methodology popularized in the early 2000s by Baudisch et al., wherein parts of the data set are selectively rendered in such a way that the parts rendered provide context for the parts not displayed. This could be applied to a raw LiDAR forest scan by providing some sort of abstract recreation of the forest, giving you structural awareness and spatial continuity without the performance cost. The question became, how do we create an abstract representation of the forest? We could simply subsample it, but this loses the precision of LiDAR, and below a certain resolution, it becomes incredibly difficult to make meaningful distinctions between point clouds of trees. Our solution was to utilize a toolkit called Forest Structural Complexity Tool. This is an open source LiDAR analytics platform which takes a raw forest LiDAR scan, segments out individual trees, and then processes them to get individual tree inventory metrics. In the process, it produces a 3D fitted cylinder dataset, which you can see in the middle there, which gives the rough position, form, structure, and taper of each tree using a fraction of the points, making it a perfect contextual dataset. So our implementation was thus: we took some raw LiDAR scans, processed them with FSCT in order to produce our focus and context datasets respectively. These were brought into Unity and rendered using a point cloud viewer asset. And in the UV information of each dataset, we tagged them as focus or context. Then at runtime, we could identify a focal area, in our case based on the position of the user's controller, and define a focus area within reach to render the focus dataset, simply by comparing the stored UV information against whether or not it's inside the focal area and discarding it if it's not focus, and vice versa. In practice, this ends up looking like this. So the FSCT dataset provides structural context and spatial continuity, while the user is able to shift their focus just by moving the controller and get a perspective on whichever part of the focus forest they want to see in real time. Because the full point cloud is loaded in memory and we're only rendering a selective amount at a time, we can keep frame rates low by limiting the size of the focal area. Because it's only limited by the amount that you can, of points you can store in memory, we were able to use our calibration data set, which was just shy of 100 million points, and selectively render this in real time in VR with no trouble. And because we're using shader code here, you can substitute the focus shape for any shape you can define with math. Based on this, we set up a variety of implementations to cover a breadth of egocentric and ectocentric techniques. So the first of these was ray lantern, lantern for its cylindrical shape, which suited the radiata pine we were assessing. Ray, as it's controlled by a raycast projected from the user's controller. Users can scale the focus size up and down discretely, which flashes up a transparent mesh, and can also lock the focus in place using the grip trigger. Next was remote lantern, which is the same sort of focus, but instead utilizes the controller's joystick in order to move it around, making it exocentric, and it could be reset to its starting position using the grip trigger. The next was the wedge light, which utilized a wedge-shaped focus projected from the user's controller, but constrained parallel to the forest floor, in which case the user can adjust the aperture and focal distance of this focus and using the joystick and reset it using the grip trigger. This was originally a true flashlight, only rendering within the projected cylinder. However, we found that though it was intuitive and it looked quite fun, in order to make meaningful structural analysis, you basically had to wave it up and down to see the full tree. So we switched to the wedge. And we also set up a control based on current industry practice, which alternated between either full context or a subsampled version of the full focus, which was reduced enough that it could be rendered simultaneously. In order to test these techniques, we set about emulating the tree selection task discussed in the introduction, wherein trees need to be identified as candidates for early harvest in order to support sustainable forest growth. To facilitate this, we tasked participants with identifying double leader trees. So this is trees where the stem splits into a Y shape partway up the trunk. We distributed a series of these around a forest grid using Poisson spatial distance sampling with some random jitter and rotation. We had about 2 dozen different preset structural models. We also asked users to differentiate between individual double leaders and clusters of double leaders, where 2 were positioned adjacent to one another. We compared their performance with each technique against their performance with the control in order to get a read on the relative effectiveness of each technique. All users had to do was reach out with the controller and squeeze the trigger when they were tagging an identified double leader, clicking once to mark it as a single leader, again to mark it as a double leader, and a third time to unmark it. We ran 24 participants using the same setup described in the previous study, and what we found is that focus and context rendering made it possible to do effective tree selection using virtual reality and LiDAR data. Specifically, the focus and context techniques were more accurate than the control. Users identified more double leaders, correctly marked more double leaders, that is, as individuals or clusters, incorrectly marked less double leaders, and had an overall higher accuracy ratio with any of the techniques than with the control, with no particular technique emerging as being best overall, so we had no interaction effect. We also found that the techniques had lower mental effort requirements, lower physical effort, higher system usability scale, and were preferred overall. My favorite bit being that of the three major techniques, they were all enjoyed pretty evenly. So though perception of assessment, the ray-focused emerged as best, given that these are all running with shader code, it's trivial to implement all three and let a user toggle between whichever one they like at any given time. Where we want to go from here is to build on these techniques. So though we are specific to forestry, these kinds of visualizations are relevant wherever dense point cloud is used in industry. So other industrial applications like time series in construction or agricultural time series would have utility for these kinds of techniques too. And they're also relatively simplistic implementations, so we want to know what else we can do with them. And lastly, we want to test their utility in a practical industry setting to get a read from the experts. So if you want to try them yourself, our OSF repo is attached with some scripts. But for now, thank you very much. It's been a pleasure to present here, and thank you for your time.
Thanks, Tim Dwyer, Monash University, Australia. Really nice talk. That was, and great work. Yeah, my question is about your rendering of the trees. The tree trunks look like they were rendered with little low fidelity cylindrical segments or something.
In the context rendering?
Yes, yeah.
Yes.
And I just wondered whether that was a design choice or an artifact of the toolkit that you're using to extract the tree structure.
A little bit of both. So the the cylindrical model coming from Forest Structure Complexity Tool isn't actually intended to be used as an analytical data set. But just by virtue of the fact that that's a necessary step in its segmentation, it gives you really nice structure. And in the case of some double leaders, it does accurately recreate it, meaning in some cases it's possible to spot out a double leader from the context data set alone. It's not perfect, but it's enough that it's better than having, just say, an abstract model there. Thank you.
Hi, I'm Tim Wesker from RWTH Aachen University in Germany. Very cool system. It looks really helpful to analyze these forest data sets. Really cool. So I was wondering, when I think about focus and context techniques in the literature, there are also some of them that adjust the layouts, the spatial layout. So like, for example, like a fisheye, you have this region and other things get squished together. Is the spatial manipulation of these trees something that you considered in this process and discarded it later on because it didn't work out well, or is this something you consider in the future?
It is, yes, not because it didn't work out well, but because with proper tree selection, you look at more than just identifying double leaders. So in the actual field process, say you need to remove 20% of the total trees in order to maintain growth at a sustainable level. If you remove them all from one corner, all you're doing is preventing increasing competition elsewhere. So you have to spatially distribute your selections. So the actual the trees adjacent to the tree in focus within an actual fair radius are as important as the tree itself. So this was to sort of keep it as useful for operationalizing as anything else.
Okay, thank you.
Thank you.
Matt Whitlock from NIST in Boulder, Colorado. Really appreciate this paper being here, just as a point cloud visualization as opposed to, say, like a data visualization or an information visualization. And I just wondered if there are any tasks or any unique characteristics about point clouds that you looked at initially that are maybe particularly unique in terms of how you might apply these visualization or these interaction techniques as opposed to, say, like a data visualization.
In this particular case, the golden goose in forestry is individual feature identification. So what would a resource forester would consider a fault being like a knot or a whirl or like a very minor visual artifact in the tree. It will come up in light art, but will absolutely not come up in something like the contextual rendering. And it's still sort of part of the field in trying to pull those out and detect those with AI. Until we can do that, being able to actually pull up the raw point cloud and objective look at it and go, oh, hey, there's a thing here, is incredibly valuable to foresters.
Thank you.
All right, last question.
Quick one, Dieter Schmalstieg, University of Stuttgart. If there wasn't any limit on GPU performance, how would you change the visualization?
Truthfully, I think because the obfuscation issue remains, even if you could display the full point cloud, you would still need some sort of technique for doing this culling, whether that's focus in context or a more advanced version of that, utilizing leveraging higher GPU limits. I'm not 100% sure, but I would probably start here.
Okay.
Well, thank you very much. All right, I wasn't able to catch them on the first when I got here, so is the presenter for the second paper here or on the Zoom ready to go? Oh, okay, we do have the author. So excellent, the second paper is Efficient and Accurate Semi-Automatic Neuron Tracing with Extended Reality.
Hello everyone, my name is Yuan. I'm excited to present our work titled Efficient and Accurate Semi-Automatic Neuron Tracing with Extended Reality, which has been accepted for the ISMAR 2024 journal track. At our big scale, we hope to explore how we can accelerate connectomic study with the help of extended reality. Connectomics aims to provide detailed map of the nervous system, showing how billions of neurons are connected and communicate with each other. Neuronal morphology, the shape and form of the neuron, plays a key role in understanding those connections. Each neuron has a unique structure, and this morphology gives us important clues about its function. It helps us determine how individual neurons send signals across the brain, driving everything from movement to memory and cognition. Here, we have a comparison of different brains, from C. elegans to humans. As you can see, the number of neurons increase dramatically. With this increase in complexity, mapping those neuronal connections become more challenging. Extracting the tree-like morphology of neuron from microscopic imaging, a process known as neuron tracing, is critical for understanding brain connectivity. Just this month, the research community completed the full reconstruction of the fly's brain. However, expanding this effort to a large brain presents significant challenges. So, we need a high throughput neuron tracing workflow. Traditionally, neuronal morphologies were manually traced by neuroanatomists. However, this approach has several major drawbacks, which limit the throughput and make it difficult to apply to large datasets. Like those of mouse or human brains, those limitations make manual tracing inefficient for modern neuroscience. Automatic neuron tracing algorithms are useful, but far from perfect. There is no universal tracing algorithm that works perfectly across different image types, modalities, or species. Each method has its limitation, whether it's noise, weak signal, or image quality variations. However, with proper manual guidance, we can help those algorithms overcome their weakness and achieve high-quality reconstructions. This combination of automatic and human inputs offer a promising solution for more accurate neuron tracing. Our solution is leverage the intuitive interaction within extended reality to create efficient and accurate semi-automatic neuron tracing. The core of our methods is using intuitive interactors, eye tracking, and gesture-based controls to guide the auto tracer. Instead of relying solely on automatic algorithm or manual tracing, we allow the user to interact naturally with the system, making the tracing process fast and more accurate. By combining those elements, we achieve a balance between computational power and human guidance, resulting in efficient and accurate semi-automatic neuron tracing. One of the key features of our system is the ability to guide regional tracing through a combination of eye tracking and hand gesture. This eye-hand interaction is crucial for refining the neuron tracing results in real time. When users notice an area where the tracing results is unsatisfactory, they can initiate what we call eye sweeping by pinching their finger and moving their eyes focus over the target region. The system dynamically adjusts the denoising threshold. This allows for real-time retracing of that specific region until the user is satisfied with the results. Once the user releases their fingers, this process ends and the adjusted region is saved. In addition to eye sweeping, the pinch gesture is also used to refine points of interest. Users first use eye tracking to quickly locate the POI, but sometimes the initial location may be slightly off. With the pinch gesture, user can adjust the position of the POI to align it more accurately with the accepted neuron structure. Once confirmed, the system updates the tracing to include previously missed branches. This seamless integration of eye tracking and hand gesture gives users precise control over tracing process, making our system not only more efficient, but also higher intuitive. We also provide several other interactors to enhance the neuron tracing process. These include tools for removing noise, isolating branches, and fine-tune arbor geometry, making the process more efficient and accurate. In order for interaction to be responsive to quickly, we present a GPU-accelerated auto-tracer. Looking at the bottom right, the table compares the execution times to the initial reconstruction and the potential path calculation between the unoptimized methods and our algorithm. In addition, our algorithm also supports incremental calculation in partial image region, resulting in failure acceleration. In order to facilitate the accurate observation and reconstruction of complicated neuronal structures, we built an immersive neuronal visualizer in our methods. Specifically, in the visualizer, we took into account several factors that are often neglected by existing neuron tracing tools. We developed a prototype of our methods with a cross-platform implementation, which is compatible with both MetaQuest Pro and Microsoft HoloLens 2. We also conducted 2 user studies to evaluate the effectiveness of our methods. In the first study, we focused on one of the key components of our approach, the eye pinch refinement technique called ER. We compared it to other labeling techniques to assess accuracy, efficiency, and overall user experience. The results clearly demonstrate that ER not only provide higher accuracy, but also offer a more user-friendly experience. This makes it most effective interaction technique among those tested. In our second study, we compared our methods with automatic following manually and other tracing techniques on the mouse and human neuron datasets. Looking at the upper left, we can see that automatic algorithms like APIP2 and R2 only perform well in certain regions. When manual guidance is added, as with AFM and our methods, the results improve significantly, with our methods providing the most complete reconstruction. In the upper right, we have a qualitative comparison across all metrics: time, deletion ratio, and accuracy. Our method outperforms AFM and other techniques, demonstrating its superior accuracy and efficiency. Additionally, we conduct a user survey to collect subjective feedback. As shown in the bottom figure, participants rated our methods higher across multiple dimensions. This feedback is further reflected in the system usability scale, where our methods scored significantly higher, confirming a more user-friendly and effectiveness experience. In summary, in this paper, we introduced a semi-automatic approach for the task of tracing neuronal morphologies from volume images. Through its novel design of a suite of interactors, an interactable neuron autotracer, and an immersive neuron visualizer, our methods effectively combine the strengths of manually and automatic neuron reconstruction approach, empower the neuron scientists to explore and comprehend neural anatomy with unprecedented efficiency and accuracy. Thanks for your listening. Please read our paper for details. Hello everyone, my name is Yuan. I'm excited to present our work.
Great. Are there any questions?
Tim Dwyer, Monash University. I was wondering about, I think one of the metrics that was presented was deletion rate. I wonder if the author could explain that a little bit.
Which metric? Excuse me. Could you please repeat the question? So I didn't get which metric were you talking about?
Yeah, I think I might have misread it. The font was very small, but one of the metrics that you evaluated your technique against, I think it said deletion rate. Deletion rate, is that correct?
Deletion, right. Yeah.
Could you just explain that?
Yeah. So we have we involve the comparison between our approach among other approaches, and the one metric we use is called the deletion ratio. Yeah, sorry for that. The font is quite small, right? So we want to demonstrate that our method is more effective than the prior works, right? Because we don't really need to delete a lot of structures. On the other hand, using the conventional pure manual tool, or using the so-called auto-opt manual approach, this curation approach, right? You have to delete a lot of unnecessary structures generated by the automatic approaches. So so our semi-automatic approach, we generate most effective and necessary structures. So we compared how many structures are first generated and then deleted.
Thank you. Any other questions? Okay, thank you again, one more time.
Thank you.
Paper 3 is investigating the effects of physical landmarks on spatial memory for information visualization in augmented reality, and it will be presented by Jiazhou Liu, and the floor is yours.
Hello everyone, I'm Jiaqi Liu from Monash University, and today I'll be giving a presentation of our work on investigating the effects of physical landmarks on spatial memory for information visualization in augmented reality. This work has been done in collaboration with Kadek and Chen from Monash University, and also Barrett from the UBC. So let's first talk about some background of this work. So augmented reality has been studied and applied to enable situated analytics, where all the information views are placed directly in the context of the physical environments or near the physical objects for sense-making tasks. Depending on the tasks, there might be, users may need to interact with multiple information views, such as texts, charts, or application windows. During these tasks, people must use their spatial skills, such as spatial memory, to navigate among these views effectively. So, what is spatial memory? Spatial memory allows people to collect and store information about their surroundings and facilitates navigation. So in the field of psychology, people invented the method of loci, also known as the memory palace, which is a mnemonic device that associates a familiar physical environment with a piece of information to enhance the recall of that information. For example, you can associate the planet names with your own kitchen, your imagined own kitchen. And in our work published at SS 2022, we investigated the effect of layout and also the effect of the virtual landmarks on spatial memory in the virtual reality environment. During that study, we could not find any conclusive evidence that the virtual landmarks has an effect on a spatial memory. However, we wonder whether the physical landmarks could have a different effect. So past works on spatial memory have been done in entirely virtual environments or physical environments. There has been little research on how the physical surroundings or the physical landmarks could have an effect on the spatial memory in a mixed reality environment like AR. For example, it would be interesting to know that in a future workspace, right, like the furniture, the equipments in the room, whether they can help you to increase the ability to recall the virtual or spatial information. This work is also motivated by another use case of a multi-view visualization. We call it small multiples visualization, where all the information views are placed in a grid layout. So in this work, we present the first empirical study to investigate the effect of the physical landmarks on spatial memory in a mixed reality environment. To design our study, we first adapted a well-known spatial memory model from psychology and discussed the potential design possibilities to position our paper. We looked into 3 aspects and discussed the relationships between them and also between the user. So first, we chose the regular office environment as our physical workspace, which is a 4x4 square meter room. And then we carefully chose 8 pieces or combinations of furniture and electronic devices as the physical landmarks, and we evenly distributed them along the edges of the room. And for information views, we adapted our work in a VR study and used a similar medium-sized virtual panel, or we call it cars, as the information views. So the cars only present black or white color because we want to minimize the effect of the semantic and symbolic on our spatial memory task. Then we recruited 16 participants and conducted a within subjects design study with 2 factors. So firstly, the first factor, we looked into whether the physical landmarks have an effect on spatial memory. So we have a study room with furniture, and the other room is empty. And we are also interested in whether the situated layout would have an effect on the spatial memory. So we have another factor where we have a regular grid layout and also an irregular furniture-aligned layout. So this 2x2 factor design will result in 4 valid combinations of factors, which were counterbalanced using a Latin square for all participants. So each participant will perform 5 repetitions for each of the 4 conditions, so resulting in 20 trials in total. To design our task, we also adapted a similar task from our VR study. We call it abstract visual pattern test. In this study, participants need to be in a room scale AR environment, and they need to learn and recall a pattern of 5 cars within 36 cars. So the 36 cars will be arranged in a 3 rows and 12 columns layout. The arrangement will be different in different conditions. For example, in a furniture-aligned layout, the distance between columns and also the height of each column will be different because we want to align each column with the furniture. And there will be 20 trials for each participant, so there will be 20 tasks, 20 patterns they need to learn and recall. So in each trial, they will go through the 5 phases in sequence from the preparation phase. So in the preparation phase, they just need to reset their position and reorient themselves, get ready for the upcoming task. And then they will move on to the learning phase, where they see and they will learn the patterns of the 5 white cars around the room. They also need to touch the car to confirm the learning. We also put a distraction phase between the learning and recall because we want to really isolate the spatial memory from the short-term memory. So in the distraction phase, we ask them to play a number typing game. So they can see the instruction on their hand and just tap the number over there for at least 15 seconds. And for the learning, we also have a constraint for 15 seconds as well. And after the distraction, they will move on to the recall phase. So they will click and review the pattern of 5 white cards from an empty grid. And the last phase is the rest. They cannot see their answer, and they just get ready for the next trial. All right, so after designing our study, we proposed 3 hypotheses. So in the first hypothesis, we say the participants will recall virtual patterns with environmental landmarks more accurately than without environmental landmarks, because we believe that the physical landmarks would have a positive effect on the spatial memory. And for the second hypothesis, environmental landmarks closely aligned with the views are more beneficial to user spatial memory than weakly aligned landmarks. We also believed that the situated layout would have a positive effect as well. And lastly, we also thought like the condition where you have the furniture and the views are closely aligned the furniture would perform the best. For example, they have the fastest recall time and also with the least mental demanding among all the conditions. Regarding the study results, there are a lot of interesting results from our study. I recommend you to read the paper for everything, but here I only want to highlight the results that are relevant to our hypothesis. For the first hypothesis, we can clearly see from our results that participants are able to recall room scale patterns of cars more accurately in a room with furniture than an empty room. So this confirms our first hypothesis. And this also aligns with other theories, for example, the method of loci. Also, from our subjective feedback from our participants, we can also see a better subjective rating, a better performance, less mental and physical demands, and also less frustration for the condition with the furniture than the empty room. For the second hypothesis, we could not find conclusive evidence that the situated layout would have an effect on the spatial memory. But interestingly, we can see that for a regular grid layout, participants will have less physical demands and also faster recall time than the other situated layout. So this implies that a regular grid layout may help the users to quickly locate the target. And for our last hypothesis, although we can find evidence that the condition has the least mental demands, but we could not find evidence that it has the shortest recall time, so we also reject the third hypothesis over there. So the main implication from our study will be furniture benefit spatial memory. It means that working in a completely decluttered mixed reality environment may not be necessary or not even particularly beneficial. So actually, in fact, the furniture are very useful as physical landmarks and can help users to create a mind map of the workspace and may enhance the efficiency of information retrieval for sense-making tasks or for browsing tasks. Also, for some latest video see-through headsets, for example, the Quest 3 or the Apple Vision Pro, they allow users to totally block out the physical environment, right? But according to our study, hiding furniture could compromise the spatial memory and may cause a poor user experience in navigating among different virtual views. We also proposed other design implications from our qualitative feedback. For example, we hope that the designers of the mixed reality application, they can allow the users to add virtual spatial reference to virtual views, or they display the virtual views in several 3x3 grid layouts. This may enhance the navigation among multiple views. And also, we hope like the designers would allow consider enabling the local motion or direct interaction for any tasks that require spatial memory. So in summary, our work proves that physical landmarks benefit people's cognitive load and spatial ability to recall the positions of virtual information views. This is also the first study to test spatial memory in a room-size AR environment. For the future work, there are a lot of interesting opportunities and directions that we can do. For example, we can test whether there will be effect on the spatial memory about like a semantic relationship between the landmarks and the information views. And also, we can test whether different relative positions between the landmarks and information views would have an effect on the spatial memory as well. And at last, we hope that this work can influence or inform the future design of the mixed reality applications. That's it for my presentation. Thank you very much.
Thank you. That was great. Does anyone have any questions?
Matt Whitlock from NIST Boulder. Really appreciated the talk, thank you. It seemed like a very conscious decision to not have the visualizations be semantically relevant. So I was curious, maybe just to speak to that and why you did it that way, and then maybe what effect that might have.
Yeah, thank you for the question. we do actually consider to have visualizations or consider the semantic relationship between the views and also the furniture. But like the focus of this work is totally on a spatial memory. If you have the visualization, if you have like some of the different visual marks or encodings, it might give you a feeling of the like symbolic effect on that. So it's not a pure like spatial memory we are testing here. So like I mentioned in the future work, yes, definitely the semantic relationship would be considered, but it has to be built upon like a ground truth, like the spatial memory itself has an effect. But yeah, cool, thank you.
Hi, Dieter Schmalstieg again. So I have to blow into the same horn as the previous question. This is a semi-abstracted environment that you used.
Yep.
I was wondering, for example, if more visual complexity of the physical environment, other than just pieces of furniture that are irrelevant to the task, but also have relatively generic shapes and so on. If you go to a really cluttered office environment, for example, also one that is maybe not because this was more or less a 360 open space. Yeah? So all of that, I understand why you're doing it like this, but what happens if we go into the complexity of the real world? Do your results transfer, or what caveats would be expected?
Yeah, thanks for your question, Dieter. I hope like everyone would have a tidy office so that they can have they can have the furniture just align the room. But yes, I understand there are situations that you have. It's like I wouldn't say it's an extreme condition, right? Like it might be common, like you have furniture inside the room, right? Because in this study, we just put the furniture along the room, which is quite arbitrary. But like, yes, if you have more complicated situation, I wouldn't say it the result will be different, because as long as you have the physical furniture that is kind of associated with the information views, you would use it as a landmark, right? So if you have a very decluttered room and you have the visualization everywhere, that probably could still be beneficial, like the furniture. Hopefully it answers your question, but we can discuss further after the break.
Yeah, I actually have a follow-up, Lisle, Virginia Tech. How would you affect user-defined layouts in the same space? How would they affect spatial memory in your estimation?
User-defined layout, you mean for the virtual views? Or?
Yeah, like they actually defined in the columns where they were in the room.
Yes, so we recommend people to align the views near the physical furniture or physical surroundings to kind of have a connection with the landmarks. Sorry, what's your question about that?
Do you think that they would users would perform better or worse if they defined where these squares tiles were in the space? Yeah, definitely. That's the recommendation from our study, right? Like we recommend them to place their virtual views along near the furniture in the room. So if it's a user-defined layout, yeah, definitely that would be beneficial.
Hi, Alejandro Martin, University of Arkansas. So just, I know this was not part of your study, but do you foresee, let's say if you were suddenly start changing the position of the objects in the scene, do you expect the users to associate that specific frame to the object itself or to the spatial position? I don't know if the question is.
Can you elaborate more on the spatial
if you were
location?
to change the monitor and put it on the place of a chair and the chair where the monitor was, do you have an expectation of whether the user will associate the square that was sitting next to the computer screen, so they will do it even though if it's at a different location?
Yeah, thanks for the question. I think it's relevant to the first question about the semantic relationship between them, right? To be honest, I don't think the participants will really, at least in this study, will really treat what kind of furniture it is, at least in these time limits. But yes, in the future, when we have a semantic relationship between the furniture and also the views, they might need to have a strong relationship. If you change the furniture away, if you swap the furniture, they might have a different effect on like information recalling. So like our vision is the semantic relationship. It definitely they have some effect, but that's the next step for this one.
Okay, thank you again.
Thank you.
And the last paper for the session is a multi-layout design for immersive visualization of hierarchical network data, presented by David Bauer.
All right. Good afternoon, everyone. My name is David Bauer. I'm a PhD candidate at the Visualization and Design Interface Innovation Lab at UC Davis. And today I will be presenting our paper. Oh, what happened? Oh, there it is. So today I will be presenting our paper, a multi-layout design for immersive visualization of hierarchical network data. I'm not sure if that works. I'll just use that's fine. So in this work, we investigate new ways of efficiently utilizing space in immersive environments to push the limits of network visualization, network data visualization. So our goal was to come up with a visualization design that embraces the space available in VR and improves the task performance for a broad range of network tasks. And to this end, we develop a multi-layout suite consisting of 4 interconnected immersive graph layouts, and each showing the graph at a different scale and catering to specific needs to solve a broad range of network tasks. So this is going to be the agenda. I'm going to briefly summarize the type of data that we deal with in this problem, how we can leverage immersive space to visualize this sort of data, and present our design and how we evaluated it. So let's get started with a brief summary of the type of data that we are dealing with in this project. And we'll build this from the bottom up, and we'll basically build a graph. So at the very bottom level of a network, we have a node. Multiple nodes can be connected with edges. And these node-edge combinations ultimately form a graph. I think that's nothing new. Now, within such a graph, we can find clusters of nodes and sort them or group them together into communities. And using, and this grouping can be pretty freeform. So we can use clustering algorithms, we can use proximity data, or we could use metadata about the graph. For example, if this is a social network, then we could use users' address information to group them spatially based on the address. So as we have larger and larger networks with more and more groupings, we might want to start aggregating them into higher level groupings. For example, these larger groups could be all the people in the same state or in the same county based on the type of grouping that we apply to our graph. And finally, we encompass all of our nodes in the network, and this way we form a hierarchy of clusters. So as you can imagine, this type of data, these hierarchical networks with group structures, they are inherently complex. And we need specialized visualization techniques and tools to explore these types of networks and to analyze them. And even with these specialized tools, analyzing and interacting with such networks can be very tedious and mentally demanding. So how can we leverage immersive space for data visualization, especially for network data like the one we just saw? So VR is a very unique environment, especially when we're talking about data visualization. Given that it's still a fairly new medium in visualization, there's still a lot to be said about its utility and best practices. So some important points that we know from prior work that pertain to this specific problem are that, first of all, the perceptual cues that display technologies, that stereoscopic viewing can offer over conventional displays is that it can improve certain graph analysis tasks, the performance in those tasks. And this fact actually had a direct influence on early studies on stereoscopic network viewing. And these studies are one of the first pieces of evidence that we have that using immersive environments for network visualization and analysis can be beneficial. Later on, these findings have been confirmed in more sophisticated studies with advanced visualization systems that fully immersed users in their data sets. And these visualizations really brought them closer to that data. And although these studies pioneered the field of immersive network visualization, very little has been done since then in terms of visual representation, interaction, and user immersion. So for a big part, these previous studies, they have used singular static layouts. They offered minimal interactivity, and for a good part, many of them rely on just the perceptual benefits of VR to kind of justify their design. So we wanted to address these limitations by introducing a multi-layered suite of immersive visualization for immersive visualization of hierarchical network data. And our main goal here was to create a visualization design that embraces the vast space that we have available in VR to improve the performance of a broad range of network tasks. And we aim to do this by introducing a suite of interconnected layouts that were designed for with immersive exploration in mind. And to this end, we tried to maximize the space utilization by using an egocentric perspective on the data, which means that in many cases, the data will surround the user and be directly accessible to the user. And in addition to that, we also leverage super and juxtaposition to efficiently utilize the space to provide users with close-ups of the data while preserving the global context within the data set. And we implement this design as a suite of 4 interconnected layouts. And each of these layouts presents the network at a different scale, emphasizing different aspects and areas of the graph. And in the following, I will briefly describe each of them. So the first view we have is the overview layout. And in this overview, the user can get a general idea of the data set and make first estimations about its size and connectivity, and the community structure, the group structure of the overall network. And in this case, communities are color-coded for easy identification. Next, we have the spherical view, which surrounds the user. And in the spherical view, nodes are placed equidistantly from the viewer, and nodes are clustered into groups. You can see that here. And here the user gets a chance to learn more about the connections between node communities. From this spherical view, users can pull down individual groups and bring them closer for closer inspection. And the selected groups detach from the spherical view and float closer to the viewer, changing the layout to make the intergroup connectivity more apparent. And this separate layout really emphasizes the intergroup connectivity while also preserving context to the network at large. So you can see that these links outwards are actually highlighted to make it clear where else they connect to other groups. And finally, a floating group can be projected onto the ground beneath the viewer. And in this fourth and final view, the focus lies mainly on the selected community. So in the context of the main network, we can see that the focus is really on a single group, and the outward connections are preserved, but in this case, much more subdued than in the previous view. And this in combination with the flat projection really allows the user to fully focus on the intergroup aspect of a cluster. And together, these 4 views form a continuous workflow from top to bottom, from focus to context, and from overview to detail. So the layouts we just saw, they're all connected with interactions that let the users select and expand groups. And in addition to that, we also offer several visual aids to help users keep focus during tasks. So let's see some examples of that. An example for interaction is selecting communities from the larger graph, in this case from the spherical view. And you can see that the links in the group are visually emphasized, and outward connections also get highlighted to allow a quick assessment of the group's connectivity. We can expand multiple groups to basically show the union of their connectivity within the larger group. Users can point at nodes to highlight their connections within the community and the network at large, which you can see in the image here. It's highlighted in orange. And finally, we use information about the hierarchical structure of the network to collect edges into curved bundles, which improves legibility of the graph. And the further the user descends into these more detail-oriented views, like the floating view or the projected view, the tighter the bundling gets to remove outside distractions. So we evaluate our design and we perform a user study. And for this study, we had 20 participants, and we compare our design against the state-of-the-art of immersive network visualization, which, in simplified terms, had a version of the spherical layout with very limited group inspection capabilities. So this is what this looked in the original paper. We do not use this exact approach. What we do is we re-implement this approach using our frameworks, offering all these visual aids that I just talked about to kind of move the focus really onto the benefit of using the multi-layout suite over just a single static layout. So the tasks that users needed to complete were selected to span the widest possible range for our study to be representative of what people generally encounter when they analyze network data. And we group our tasks into 3 categories: intra, inter, and epi-community tasks based on their scope. So intra-community tasks were limited in focal and spatial scope, and users only needed to focus on a single group or community of nodes. An example for this would be to find common neighbors of 2 nodes within a group. Inter-community tasks require a broader scope of regard, and users typically need to focus on several groups at the same time in order to solve these. And lastly, epi-community tasks require attention to the full scope of the network. These usually involve many or all the groups in the network, or just the whole network at large. So how did users perform in this study? Just to summarize a big table of numbers. Overall, we saw significantly higher task accuracy in the majority of tasks. Only the inter-community tasks lagged behind a bit in accuracy. And we found no significant difference in task completion times. So basically, we can say that using our design, people solve tasks more accurately using no more time than the state-of-the-art in immersive network visualization. So we were also interested in how people felt when using our design or after using our design. So we asked them for structured feedback. We used the NASA TLX questionnaire to determine that. And in our case, people felt that using our design was less physically and mentally demanding than the baseline, which was the state-of-the-art. They felt less irritated overall. They also felt more relaxed when completing the tasks. And ultimately, this resulted in them feeling significantly more confident in their task performance. And with this, I want to wrap it up and summarize our contributions. So in this work, we introduced a new visualization design for hierarchical network data in VR. To this end, we develop a multi-layered design of interconnected immersive graph layouts to cater to varying spatial and focal requirements when analyzing such tasks. This is what it looks like in practice. And to validate our design, we conducted a user study comparing against the state-of-the-art of immersive network visualization. Our findings suggest that users perform better and are more satisfied when using our design. And we hope that our results will inspire future research into efficient space use and network visualization for network visualization in VR and into immersive visualization at large. And this marks the end of my presentation. I want to thank you for having me, and I'm happy to answer questions. And I want to add, I'm happy to say that this project has recently been picked up by a new group of students in our lab, and we will be releasing code base for public access in the future. So thank you.
Excellent. Are there any questions?
Hi, Tim Dwyer, Monash University. Thank you, very nice. I missed a little bit exactly what the baseline in your study was. You said it was the state-of-the-art network visualization. Could you just explain what the comparison was exactly?
Yeah, so the baseline, I had this small icon representation of those. So the baseline was based on a paper by Guan et al. From 2016. And what they did is basically offered something that is this is actually the inspiration for the spherical view that we have. They offered something that's very similar to the spherical view. And what they had is they had this graph available in VR, and users were able to highlight groups by basically when you highlight groups, it would like slightly move towards you, but it would not change in layout or anything. So this is when we say group inspection is limited. It basically means like it visually enlarges the group, but it doesn't really change anything about its appearance. So the baseline for our design, comparing our design was this, but we implement this type of layout and this type of interaction with our framework because we wanted to make sure that we compare the multi-layout aspect of this design against the baseline and not maybe this highlighting or any of these other visual aids help in the task, but we wanted to avoid that, so we re-implement this in our framework.
Any additional questions?
I'm just curious about your premises of using a hierarchical graph. Not every network is hierarchical. You must have had something in mind about the semantics of a certain application area that use networks.
Yeah, so I think there can be two avenues we can take with this type of data. One could be pre-annotated, where the hierarchical structure is inherent to the data. And another one could be where we use clustering algorithms to create the hierarchy artificially. So this could be, for example, neuron data. One of the papers earlier mentioned neuron tracing, neuron data. We actually use a neural network, not the machine learning one, the actual biological one. And we use artificial clustering to create functional groups within that brain data. And other networks might have some inherent property, like social graphs, for example, based on people that are connected and people in the same area. These structures could already be in place. So depending on which type of data you have, the kind of motivation for using such a system might differ. So one way you create the clustering, it might be more of an exploratory task that you have in mind. And for data where these structures are already in place, you might want to find specific insights, like the properties of well-connected people in a social graph, for example. Then you could use those hierarchy and this hierarchical data to kind of go from there and go with the tasks. Something interesting, sorry, I just want to add this to this answer, is that in this study, we only really use the lowest level of the hierarchy to find these like low-level groups that we can expand and interact with. It would be really interesting for future research to make use of the full hierarchy, multiple levels that we have.
Okay, thank you very much.
Thank you.
That concludes this paper session, and I hope everyone enjoyed those 4 quality presentations.